Okay, we have exercises 13, 15, and 17 here in chapter 4, and I'm going to actually use my notes on these just so you have a little more detail. So in example 13, we have a salesman with two appointments. Either one, there is if they make a sale, there's a 50-50 chance of selling a $1,000 encyclopedia set or a $500. But we don't know that this salesman's going to make a sale. In fact, the first attempt, there's only a 30% chance. Second one, there's a 60%. So we're looking, first of all, what is our X? And it gives us, in this case, X is the total value of all sales. But I do want to bring out the point that you should think carefully what your random variable actually is as you're approaching these problems, because in many cases, there's multiple ways to define it. Oftentimes, they can each lead to correct solutions, but some of them are much clearer and quicker than others. But in this one, we're given it. X is the amount that is actually made. So if you think about it, what would be the lowest that the salesman can make? Well, if neither of the sales worked out, that would be $0 total earned. Another option would be they sell one of the cheap encyclopedias, but nowhere, or don't sell anything on the second one, which would be 500. The most that they'd be able to sell is 1,000 in each appointment, so that would be a $2,000 total. And if you go through them, you can see that every $500 increment there, the salesman would potentially be able to get. Now, certainly not equally likely, and that's the next step. So we want to calculate for the PMF the probability of getting each one of those individual X values. So notice for getting 0, in order for that to happen, as we go through these, essentially what we're asking is how many different ways could we get 0, and then calculating the probability for each of those separate ways, then adding those together. So for 0, there's only one way. It doesn't get this one, so that would be a 0.7 chance, because there's a 0.3 chance of making the sale, so 0.7 of not getting the sale, 0.4 of not getting the sale here, which would be 0.28 total. 500, now we have two ways. They could do no sale and then 500, or 500 and then no sale. So we have both of those accounted for here. 1,000 is the most difficult because we could get 500, 500, or we could get 1,000, 0, or 0, 1,000. So there's actually three different ways we need to account for. And you'll notice that when we're looking at getting the 1,000 here, we have to make the sale, getting the 500 in each. We have to make the sale, and then sell the 500, make the sale, sell the 500. So there's actually 4 different steps that need to happen to get that 500-500 split. So we add all those up. These should add up to 1 because we're accounting for all the possible values of X, and they do. Example or exercise 15. Okay, so we have the the NBA draft basically, and I'm not real familiar with the draft to know if this is actually how it's done, but it seems pretty cool if it is. So we have 66 balls. 11 balls have the name of the worst team from the previous year. 10 have the name of the second worst team, and so on up until the 11th worst team from the previous year only gets 1 ball. So why the different number of balls? We're trying to even out the teams basically by giving the worst team the best probability of getting first choice. So we notice here that there's only the worst team could only have 4 options for the draft pick. Either they get chosen in the first, second, or third selection of the basketball, or if they don't get it by the third, they will automatically get it in the fourth, because after 3 draws of the basketball, they just go down and assign in order, starting with the team that was worst, the remaining draft picks. So if no one's gotten it yet, then the 11th will get it right here. Or the worst team would get the 4th pick. Okay. Let me rephrase what I just said there. For that 4th, what that means is if the worst team hasn't been selected in the first 3 draws, it will automatically get selected in the 4th draw. I don't think that was real clear with what I just said. Okay. So what's the probability that this worst team gets chosen in the first round of this basketball selection here? Well, they have 11 balls in the lot and 66 total balls, so 1166 or 1/6. That one's pretty straightforward. Starting with the probability that they get second, it gets much more complicated because remember, let's say that the 5th worst team gets chosen. So they would have, I guess that would be 6 basketballs in the pick, and one of those 6 gets chosen in the first selection. Well, now we're essentially going to take those other basketballs out of the round. They don't actually remove them, but if one of them gets drawn, it's just counted as not counting. So essentially, the rest of those 5 balls are gone, which would mean in that case there would be 60 balls remaining. But we don't know. It could have been a different team. It could have been the 11th worst team who only has a single basketball that was chosen here in this first round, in which case there's 65 active balls still remaining. So because we don't know, we have to take a sum of all those possibilities. So J represents the how bad your team was. J equals 1 would be the worst team in the league. We're not counting them here because we are the worst team. In this problem, we are the worst team. And here we're just looking at what's the chance that one of the other teams got chosen. Because we clearly didn't get chosen in the first round if we're getting the second round here. So we start here. If J equals 2, that would be 10 over 66. If J equals, say, 11, in other words, the 11th worst team, we would only have 1 after 66. Notice that each of these is going to be the probability that that team was chosen in the first round. And if they were chosen, we want to know what's the probability that they were chosen, And here we have 11 over 54 plus J. Where is this 54 coming from? Notice that we're taking that away, 12 away from 66, or more precisely, we're taking 11 away from 65 and adding there. So the second worst team, 1066 over 1156. That means this is the chance that second worst team got chosen in the first round. This is now the chance that our team, the worst team, gets chosen in the second round. We need to know how many balls are left here. The third, it gets pretty complicated. Essentially, we're going to have to do that. We're going to have to account for all the possible teams that could have gotten chosen here and all the possible teams that could have gotten chosen here. So we still have that summation from probability x equals 2, but we also have to throw in a second summation to now account for the team that got chosen in the second round. It wasn't us, because at this point we're calculating the chance we got selected in the third round. So we have to account for everyone except for ourselves. That's why we don't take k equal 1, and we don't take k equals j, because whatever j was would have gotten chosen here in the second round. So except for those two, we're going to go through all the possible teams. Now, probability of 4 would be really complicated. We'd have a triple summation, except that we realize these are the only possible values of x. The probability of each of them, when we add them up, has to equal 1. And so we can take 1 minus f. So what's this capital F? This is the CDF. In other words, another way to write this is the probability that x is less than or equal to 3. So essentially we're adding these three probabilities up, subtracting that from 1. The only thing that's left is the probability that x equals 4. Okay, and then we finally get to 17, which is an interesting distribution function, because what we have here is a mixed discrete and continuous distribution. If you didn't pick that up by looking at the different values of the CDF, what's happening is we're going along kind of a line like this, then we have a jump, and then we're going along and then have a jump. Whereas in class, what we had looked at for a CDF for a discrete is we're just going along straight, and then we have a jump, and we're going along flat, I guess is a better word, and then we have a jump, flat, jump. In other words, the only places we're gaining probability is at discrete locations. Whereas here, we're constantly gaining, and then we still do have some discrete jumps. So how do we know how much we're actually jumping at these points, at x equals 1, x equals 2, and x equals 3? Well, we look at what it is from the left-hand side. In other words, when b is between 0 and 1, so we're using b instead of x here because it's varying. And if b is less than 1, it's divided by 4. So right when we get to the point where b equals 1, we would have 1/4. Okay. However, if we look when b actually equals 1, we see that the formula is now 1/2 plus b minus 1 over 4. In other words, 1/2. So this f function, this CDF, jumps from a value of 1/4 to 1/2. There's a jump discontinuity right there, and it gains 1/4 right there. 1/2 minus 1/4 gives us 1/4. And that gain is coming in from the probability that x equals 1. So there's a stronger probability that x actually equals exactly 1, and we can calculate that to be 1/4. At 2, we have a similar thing coming in from the left. We would have gotten 3/4 had it continued, had it kept its continuity. When it jumps, it actually gives us 11/12, so we subtract what it should have been if it was just staying continuous versus what it actually was, and that gives us a difference of 1/6. And then finally, the final jump goes from 11/12 to 1 to give us a 1/12. So we have the discrete probabilities at those three values of x for part A. For part B, we want to know the probability that x is between 1/2 and 3/2. Now notice that there is no specific jump at 1/2 and 3/2. How do I know that? Well, if you look at how the CDF is defined, the only potential jumps come in at 0, 1, 2, and 3, where there's, and it doesn't even mean there is a jump there, but those are the only potential breaks in the continuity. So 1/2 and 3/2, it doesn't really matter if we include those points or not. That's the point I'm trying to make here. So how would we get in between? Well, we would take the CDF all the way up to 3/2. So that gives us the probability that x is less than or equal to 3/2. And then subtract out the part that we don't want all the way up to 1/2. So this will give us the probability between 1/2 and 3/2, which we can calculate to be 1/2.